In the last video, we started talking about logarithms. And remember, a logarithm is just an inverse function of an exponential function. It undoes the work of exponentiation. So exponentiation kind of blows things up. Logarithms shrink things down. Now we had talked about how for logarithms, a should be positive, the base should be positive, and it should not be equal to 1 just because it's not really useful when it's equal to 1. Alright, now there's some properties of logarithms that we've already experienced in some way, but we just want to sort of make them clear in general now here. So let's go through these first few together. We have, for any a that's greater than 0 and not equal to 1, log base a of 1 is equal to what? Well, remember, you should be thinking to yourself, what do I need to raise a to the power of to get 1? And this is only going to work, this always works, when your exponent is 0, because any non-zero number raised to the 0 power gives you 1. And so log base a of 1 is always equal to 0. Alright, what about log base a of a? Again, you should be thinking to yourself, what do I need to raise a to the power of to get a? Well, it's already kind of equal to a. I don't really need to raise it to any power, and so we can always just put an exponent of 1 here, which means log base a of a is equal to 1. And that's going to be true for any a that's positive and not equal to 1. Alright, log base a of a to the x. Well, again, you should be thinking to yourself, what do I need to raise a to the power of to get a to the x? Well, that's going to be x, right? A to the x is equal to a to the x. And so this gives you x. And remember, this fits with what we said because we need these two functions to be inverses of each other. If we plug one function into the other, you need to get whatever your original input is out again. In other words, log base a of a to a power, they kind of cancel each other out and you're just left with x. Similarly, a raised to the log base a of x power should just give you x. Right? These cancel each other out because they're inverses of each other. But there's some other sort of more interesting properties here. The product, quotient, and power property. And these, unfortunately, are not what you might think they would be. If you have log base a of a power, x times y, then it's not going to be the case that this is equal to, log base a of x times log base a of y. That might be what you think, that it just sort of distributes nicely like that, but it's not the case. It turns out log base a of x times y is equal to log base a of x plus log base a of y. So if we want to split that product on the inside up into two separate logs, it's going to be addition in the middle instead of multiplication. And similarly, using similar reasoning, log base a of x divided by y, we can break this up into two separate logs as log base a of x minus log base a of y. And we're going to see in a minute why this is true. Finally, if you have log base a of x raised to the y power, again, you might be tempted to pull that y out in front, but in fact, that's not the case. In fact, log base a of x to the y power can be rewritten as y times log base a of x. So in a sense, you can take that exponent of y and just pull it out in front as multiplication. This seems a little unusual at first, and it's easy to get these properties wrong, but we'll try to understand why these properties hold by looking at a few examples. So let's start with log base 2 of 16 times 4. I'm going to compute this in two different ways. So one way to think about this is to say, well, this is log base 2 of, 16 is 2 to the 4th power. I'm trying to rewrite it as powers of 2 just because it's easier to compute logs that way since my base is 2. And 4 is 2 to the 2nd power. So I could write this as log base 2 of 2 to the power of 4 plus 6. 4 plus 2. Right? Because this is how multiplying two exponents with the same base works. You add the exponents. This is equal to log base 2 of 2 to the 6th power, which is equal to 6. Well, notice that's the same thing you would have gotten by computing these as two separate logs, log base 2 of 16 plus log base 2 of 4, adding them together. Because log base 2 of 16 is just 4. Right? 2 to the 4th power gives you 16. And log base 2 of 4 is just 2. Right? So this is really trying to get at the idea of why we can break this up into the addition of two separate logs. Because remember, these logs that you're getting out at the end, they're exponents. And when we multiply two terms, we add the exponents. That's why when we break this up into two separate terms, we're going to add them together, because each of these individual logs are representing exponents. When you multiply two terms, you add the exponents. All right. Similarly, if we wanted to find the log base 3 of 81 divided by 3, well, I could rewrite this using powers of 3 as follows. We have log base 3 of, 81 would be 3 to the 4th power, because it's 3 times 3 times 3 times 3, 9 times 9. And 3 in the bottom, I can rewrite it as 3 to the 1 power. So inside my parentheses here, I could rewrite this as 3 to the power of 4 minus 1, which is 3 to the 3rd power. Oh, whoops. I still got a log on the outside. Log base 3 of 3 to the 3rd power. And of course, log base 3 of 3 to the 3rd power is just 3. But that's the same thing I would have gotten if I had written this as log base 3 of 81 minus log base 3 of 3. Because log base 3 of 81 is equal to 4, and log base 3 of 3 is equal to 1. So in either case, we get 3, which is trying to show you exactly why we would subtract. Right? Remember, these logs are exponents, and when you divide two powers that have the same base, you subtract the exponents. So when we break this up into two logs, we're going to subtract them. Finally, consider log base 5 of 25 to the 3rd power. Let's see if we can compute what this would be. Alright, I'm going to start by trying to rewrite the inside as a power of 5. Well, 25 would be 5 squared, so I could rewrite this as 5 squared to the 3rd power, which is like saying log base 5 of 5 to the power of 2 times 3, because we multiply exponents when you have a power raised to another power. And so this, of course, is equal to 6, because 5 to the 6th power gives you 5 to the 6th power. Right, this is the same thing you would have gotten if you had just pulled that 3 out in front to begin with. 3 times log base 5 of 25 would be 3 times log base 5 of 5 squared, which is 3 times 2, which is 6. Okay, so these examples should give you a sense of how or why these properties hold for multiplication, division, and exponentiation of logs. Alright, so we're going to apply these properties now. So what we're going to do is try to use the properties to compute these as much as we can. Alright, so we have, well, I'm not really sure what this example was supposed to get at here. Hang on. Alright, how do we expand ln of 6? There's nothing really going on in there, but I guess one thing we could do is we could rewrite 6 as a product of, say, 3 times 2. And then we could apply the product rule. Multiplication on the inside is like addition on the outside. So this is equal to ln of 3 plus ln of 2. That's one way you could rewrite it. There's other ways as well. For question 2, we have ln of 2 divided by 29. This is division on the inside. That's equivalent to subtraction on the outside. So this is equal to ln of 2 minus ln of 29. According to so this was by the multiplication property. This is by, we'd call that the quotient property. Alright, how do we simplify number 3? Well, I can't really use addition or multiplication, or the multiplication or quotient properties here, but what I could do is I could rewrite this as, inside the parentheses, as 5 to the 1/3 power. Rewrite that radical as an exponent. Now using, say, the power property, I can pull that 1/3 out in front and multiply by log base 5 of 5. Remember, the power property says if you have some sort of power inside your log function, you can pull it out in front as multiplication. So I can rewrite it as 1/3 times log base 5 of 5. Well, log base 5 of 5, if we go back to our first page of properties, log base a of a is always equal to 1. So log base 5 of 5 is equal to 1. So this is 1/3 times 1, which is just 1/3. Okay, this simplified nicely. Let's try number 4. We've got ln of 2 over e to the 6th power. We've got a quotient inside, so it would make sense to use a quotient property here. Division on the inside means subtraction on the outside. So this is going to simplify to ln of 2 minus ln of e to the 6. Okay, that was by using the quotient property. Now, if you wanted, you could use the product property to pull that exponent of 6 out in front. But remember, ln just means log base e. So this is ln of 2, which doesn't really simplify nicely. It's a number, but it's not a nice whole number. But ln of e to the 6 means log base e of e to the 6. So this is just going to be equal to 6. Ln of e to the 6 is just plain 6. All right, let's try number 5. We've got log base 4 of 5x cubed times y. You might be tempted to try to pull this exponent of 3 out in front, but that doesn't really work here, at least not yet, because it's not the entire function that's being raised to the 3rd power. It's not all of 5xy being raised to the 3rd power. It's just x being raised to the 3rd power. So the power rule wouldn't really work here just yet. But we could use that multiplication property to break this up into 3 different logs, because I'm multiplying 5 times x cubed times y. So I can rewrite this as log base 4 of 5 plus log base 4 of x cubed plus log base 4 of y. And now, if I wanted to, I could rewrite this one more time. I have an exponent of 3 in here. I can pull that out in front as multiplication and rewrite this as log base 4 of 5 plus 3 times log base 4 of x, and finally plus log base 4 of y. There's nothing else really to compute here, but this was by the power property. And finally, using similar reasoning, I can break up this last log into 3 separate logs. It's multiplication inside, so that's addition outside. Log base 2 of 4 plus log base 2 of x plus log base 2 of y to the 5th power. And does this simplify any further? Yeah, it does, because, well, first of all, log base 2 of 4 is just a real number. What do we have to raise 2 to the power of to get 4? 2. 2 squared is equal to 4. So log base 2 of 4 is just 2. Log base 2 of x, there's nothing for us to do here. But in this last term, we have log base 2 of y to the 5. I have an exponent on the inside. So using the power property, I can pull that out in front as 5 times log base 2 of y. So for this, we use the product and the power. Oh, I guess we didn't call it product property. We called it the multiplication property. The multiplication and the power properties. Okay, now why is this useful? I mean, in some sense, we were able to simplify this a little bit, but it's not necessarily clear why this is going to be useful to us. So to give you an example, let's say for some real numbers a, b, and c, we knew that the natural log of a was 6, the natural log of b was 3/2, and the natural log of c was 7. Now, I don't know what a, b, and c are. I just know the value of the natural logs of those numbers. But knowing that is enough for us to compute more complicated expressions like ln of square root of a times b squared over c cubed. Here's how we could do that. First, I'm going to rewrite this, getting rid of the division on the inside. So using that quotient property, is that what I called it? Okay, quotient property. Division on the inside is like subtraction on the outside. So I can rewrite this as ln of square root of a times b squared minus ln of c cubed. Now let's break up this first log. We've got multiplication on the inside, so I can rewrite that as addition on the outside. Ln of square root of a plus ln of b squared minus ln of c cubed. Now I don't actually know the values of any of these yet, but I can get rid of the exponents, or in the first case I can rewrite this as ln of a to the 1/2 and then get rid of the exponent. To rewrite this one more time as pulling each one of my exponents out in front as multiplication, I can rewrite this as 1/2 times ln of a plus 2 times ln of b minus 3 times ln of c. And I can find the exact value of this because I know that ln of a is equal to 6. And I know ln of b is equal to 3/2. And I know, let's try orange, ln of c is equal to 7. So rewriting this one more time, I can get rid of the ln's altogether, and I have 1/2 times 6 plus 2 times 3/2 minus 3 times 7. So I get a whole real number, well, not necessarily a whole number, but I get a real number in the end. 1/2 of 6 is 3, 2 times 3/2 is 3, and 3 times 7 is 21. So I get 6 minus 21, which would be negative 15. Alright, so knowing those different properties of logs allow us to do these more complicated computations. Okay, now we can also do the same process in reverse. So we can take a logarithm that's been expanded and condense it into one single log using those exact same properties. Let's do a few examples. So we start with 1/2 log of x plus 3 log of x plus 1. Alright, let's think about what we can do here. We can take any coefficient on the outside. Different color here. Right, if we're multiplying by a constant on the outside, we can move that in as an exponent on the inside. So I can rewrite this as log of x to the 1/2 plus log of, be careful here, that whole inside term x plus 1 is going to be raised to the 3rd power. And now, because I have an addition of 2 logs with the same base, there's nothing there, so we can assume it's base 10. I know that addition on the outside means multiplication on the inside. So I can rewrite this as log of x to the 1/2 times x plus 1 cubed. Or if you prefer, x to the 1/2 is the same thing as just saying square root of x. That would work as well. So this is a way of rewriting a complicated looking log as just one single logarithm. Alright, let's do that again in 2. This time we have a 1/3 on the outside, and then inside brackets we have log base 2 of x plus log base 2 of x plus 1. So what I'm going to do first is I'm going to use that product property, the multiplication property, to combine the inside into one single log. So we'll have 1/3 on the outside, and then inside, addition is going to mean multiplication. Addition on the outside is multiplication on the inside. So this will be log base 2 of x times x plus 1. Because we take whatever's on the inside and we multiply them together. And now I can take my coefficient on the outside and move it inside as an exponent using the power rule. So I can rewrite this one more time as log base 2 of x times x plus 1, all raised to the 1/3 power. Oof, this is messy. Just make sure it's clear that that 1/3 power is inside the log function and not outside. So just put one extra set of parentheses in there to make it clear. Alright, let's do this again. We have 2 ln of x plus 2 minus ln of x. I'm going to get rid of this coefficient of 2 first by bringing it inside as an exponent. I can rewrite this first term as ln of x plus 2 squared we still have minus ln of x. Notice that x plus 2 is all being raised to the second power, and all of that is inside a set of parentheses for the natural log function. So the exponent goes inside the log function. And now, because I'm subtracting two logs that have the same base, namely ln of x plus 2 squared minus ln of x, subtraction on the outside is the same as division on the inside. So I can rewrite this as a single log ln of x plus 2 squared over x. Right, x plus 2 squared came from the first one, and x came from the second one. Now finally, for example 4, we have log base 2 of x plus 2 times log base 3 of x. Alright, how do we combine these? We don't. Do not combine because they do not have the same base. You can't combine them. They need to have the same base in order for any of these properties to apply. So there's no way to combine these two. Alright, now if you have something that's in a base that's not desirable for some reason, for example in the last example, maybe you wanted to try and combine those two logs but they have different bases, so you want to rewrite one of them in the same base, or maybe because you're trying to work on a calculator and your calculator only has log base 10 and log base e. Well, we have a formula, the change of base formula, that allows you to rewrite a logarithm with a new base. So let's look at a couple of examples. If we wanted to rewrite log base a of x in base b, you use this formula right here. So log base a of x is going to be equal to log base b of x divided by log base b of a. So this is what I'm going to do. For each one of these problems, I'm going to write what's my old base, that's your a. So my old base is 4. That's the base that I'm originally have my log expressed in. B is my new base. They're telling me that I want that in base 10. So according to this formula, log base 4 of 25 is going to be equal to log with the new base, so log base 10 of whatever was originally on the inside. I guess I should have said my x is 25. So log base 10 of 25 divided by log base 10 of whatever a was. That's 4. Alright, well, whatever this is, it's now written in your new base. Let's try number 2. Log base 2 of 12, we want to rewrite it in base 10. So the old base is 2, the new base is 10, and the x, the inside term, is 12. So the change of base formula tells us log base 2 of 12 is going to be equal to log with the new base of 12 divided by log with the new base of the old base. So log base 10 of 12 over log base 10 of 2. Alright, running out of space here, so let's try number 3 down here. For number 3, we have that our old base, a, is 4. Our new base that we want to write it in is base e. And our inside term is 25. So this says that log base 4 of 25 is going to be equal to log base e of 25 over log base e of the old base, 4. Okay? And finally, for number 4, oops, oh, don't do that. For number 4, we want to rewrite log base 3 of e to the 4th in base e. Okay, so our old base, a, is 3, our new base is e, our inner term is e to the inner term, x is going to be equal to e to the 4th. So log base 3 of e to the 4th should be equal to log with your new base of e to the 4th over log with your new base of your old base. And actually, the top here is going to simplify. Log base e of e is just 1, or log base e of e to the 4 is just 4. So this is going to be 4 over log base e of 4. Or if you prefer, remember log base e you can always rewrite that shorthand as ln of 4. In the next video, we'll talk about solving exponential and logarithmic equations.